Good afternoon, everyone. Welcome to today's presentation for Chapter 6, Creation and Enrichment for Knowledge Craft class. Today's presenters are Mo Yerimnim, San Inteknim, and Soundarya, that's me. In today's presentation, we'll introduce principal techniques that are used for creating knowledge graphs and how they can be further enhanced from a myriad of legacy data that ranges from plain text to structured formats. Then we'll discuss an apt methodology to follow when creating a knowledge graph that depends on the actor, domain, on-researched applications, available data sources, etc. So, this is the outline for today's presentation. I'll be covering human collaboration and text sources. San Inteknim will cover markup sources and partially from structured sources. The remaining part of structured sources will be covered by Mo Yerimnim, as well as the last section for today's presentation, schema or ontology creation. In order to create knowledge graphs based on text, human collaboration is pivotal. There is one such approach for creating and enriching knowledge graphs, that is to solicit direct contributions from human editors. Example would be an in-house, that is example employees of the tourist board, crowdsourcing platforms, feedback mechanisms, example tourists writing reviews on attractions that they visited, collaborative editing platforms such as Google's Freebase and Wikimedia's Wikidata. These are well-known knowledge bases. To give an example, let's take South Korea. South Korea is getting popular because of Hallyu. Let's take an example of South Korea. South Korea is getting popular because of the Hallyu, and for in-house, that is employees of the tourist board. Let's take Gyeongbokgung Palace. And crowdsourcing platforms such as My Real Trip engage in attracting foreigners to visit Gyeongbokgung Palace. And after foreigners come to Korea and visit the palace, they write their feedback on TripAdvisor. Then also on collaborative editing platforms such as Wikimedia's Wikidata and Google's Freebase. Since here the public people can publicly edit it, it gives rise to some disadvantages that we'll discuss. But first, human involvement incurs high costs for well-known knowledge graphs that have been primarily based on direct contributions from human editors. The drawbacks are it gives rise to human error. Here, human error would be there might be false information about a particular attraction here in Seoul, here in South Korea, and it leads to controversial and peaceful articles. Then we analyze the temporal characteristics of the activity in these samples. When we analyze it under short time scales, it gives rise to conflict and disagreement of activity patterns, and that gives rise to bias when it kind of becomes difficult to distinguish between what is true and false. and that leads to vandalism that takes place from this controversy. Therefore, it leads to challenges in licensing and tooling. Here, licensing and tooling is with the success of Wikidata from Wikimedia. Google also decided earlier in 2014 to offer the content of freebase to the Wikidata community. But there were some ongoing transfer efforts, data mapping challenges, and that gave rise to licensing and tooling problems. And primary sources tool aims to facilitate this problem and help in future data migrations between Google's Firebase and Wikimedia's Wikidata. Therefore, it leads to employment of humans to verify and curate additions to a knowledge graph that are extracted by external means. For example, like video games with a purpose, defining high quality mappings, or illustrating appropriate high level schema. And this image is introduces on how to craft a knowledge graph based on semantic data modeling way. That is, first step, you need to clarify your business data requirements and then gather and analyze relevant data and ontologies, which are domain, scope, genesis, and then to maintain it and maintenance. Then, since it's unclean data, unstructured unclean data, you need to clean your data to ensure good data quality. Now, let's move on to the next section with text sources. Here, we'll introduce principal techniques on how to build knowledge graphs from text. Here, Text Corpora is a language resource consisting of large and structured set of texts from newspapers, books, scientific articles, social media, emails, web crawls, etc. And for extracting it with high precision, for creating or enriching a knowledge graph, it becomes a non-trivial challenge. Therefore, techniques from natural language processing, NLP, and information extraction are used. Let's introduce the first technique used for building knowledge graphs from text, which is pre-processing. Here, pre-processing involves applying various techniques to the input text. If you look at figure 6.1, it illustrates tokenization that parses the text into atomic terms and symbols. Here, the text is Santiago has flights to Rapa Nui, which was named on the World Heritage Site in 1995, and that is parsed into atomic terms and symbols. If you look at this part here, named entity recognition, NER, entity linking, EL, relation extraction binary RE, and NRE are different types of techniques that are used for constructing knowledge graphs from text that we'll be discussing today. There are also other pre-processing tasks such as parts of speech (POS), which are used to identify terms representing verbs, nouns, adjectives. Is another task of dependency parsing that extracts a grammatical tree structure for a sentence where leaf nodes indicate individual words that together form phrases. There are, for example, noun phrases or verb phrases, and clauses and dependency parsing also extracts clauses and sentences, and word sense disambiguation, WSD. Here, WSD is used to identify the meaning in which a word is used. Typically, words have different meanings, and based on how you use it in a sentence, the entire meaning of that phrase changes, right? Therefore, WSD helps in linking words with the lexicon of senses. For example, let's take word net and BabbleNet. In WordNet, in BabbleNet, the term flights may be linked with the word net, an instance of traveling by air, rather than a stairway between one floor and the next. A stairway between one floor and the next means a flight of stairs. Flight of stairs is a collective noun. Here, in this collective noun, flight means describing a stairway between one floor and the next. But flight also means traveling to different places around the world by air. Therefore, to solve this problem, we need to use an appropriate type of pre-processing that often depends on the requirements of later tasks in the pipeline. Therefore, we introduce named entity recognition, that an NER. There are three major approaches to NER, that are lexicon, rules, and machine learning. Here, NER identifies mentions of the named entities in the text that are typically targeting mentions of people, organizations, locations, and other types. NER has multiple modern approaches that are based on learning frameworks that support lexical features, for example, parts of speech tags, POS, that we introduced earlier, dependency parse trees, etc., and gazetteers. Gazetteers is a record that contains lists of common first names, last names, countries, prominent businesses, etc. Here, these supervised methods require manually labeling all the entity mentions in a training corpus. And training corpus, and if you, is given here in figure 5, where we'll discuss the NER pipeline that I got from chapter 3 in Big Data Analytics or Social Media textbook. Here, a corpus is a language resource that consists a large and structured set of texts, and it's first tokenized, that we introduced earlier, where a sentence is parsed into atomic terms and symbols. The sentence is split, and feature is extracted, then the model is applied and data is tagged. After the model application, we use post-processing, tag data, and here NER comes into place, where mentions of people, location, organizations or events are labeled manually. There's another approach called bootstrapping based approach that requires a small set of seed examples of entity mentions from which patterns can be learned and applied to unlabeled text. There's distance supervision, which uses known entities as seed examples through which similar entities are detected. But apart from these learning-based frameworks, We can also use traditional approaches which manually crafts rules, and sometimes they're still used nowadays because of their controllable and predictable behavior. If we look at figure 6.1, the named entities identified by NER, such as Santiago Rapa Nui World Heritage Site 1995, here it may be used to generate new candidate nodes for knowledge graph. Next is entity linking. The EL task associates mentions of entities in a text with the existing nodes of a target knowledge graph. This is also known as the nucleus of a knowledge graph under creation, or an external knowledge graph. But it also gives rise to challenges when you associate mentions of entities in a text with an already existing node of a target knowledge graph. That is, both Rapa Nui and Easter Island has different ways to represent the same entity, but the same mention in different contexts can refer to distinct entities. For example, Santiago can refer to cities in Chile, Cuba, Spain, among others. An EL task here is to consider a disambiguation phase wherein the mentions of the candidate's rank and the most likely node, whether Santiago refers to Chile, Cuba, refers to cities in Chile, Cuba, Spain, is chosen. Here, the context can be used in a phase where an appropriate candidate is chosen for the mention. If you look at figure 6.1, we assume the nodes Santiago, Easter Island, Santiago, Easter Island already exist in the knowledge graph, and then you link them. Next is relation extraction, RE. The RE task extracts relations between entities in the text. There are also other learning-based approaches that we'll use again, that was introduced earlier in named entity recognition, such as bootstrapping, which requires a subset of manually labeled seed examples, distance supervision, that finds sentences in a large corpus of text mentioning pairs of entities with a known relationship or edge, which are then used to learn patterns for that relation. Here, binary RE can also be applied for using unsupervised methods in an open setting called open information extraction, also known as OIE. OIE is a set of target relations that are not predefined but rather extracted from text base. For example, dependency parse trees from which relations are taken. Here, in figure 6.1, it shows an n-array. If you look at this part here, it shows an n-array relation capturing additional temporal content. Here, resources such as FrameNet, as the name suggests, defines frames for words and then identifies the semantic frame for it, which includes speaker, that is the person who names something, an entity, an object that's named, and a name. Here, FrameNet is a research and resource development project based at the International Computer Science Institute in Berkeley, California, which produces an electronic resource based on a theory of meaning called frame semantics. For example, here if I say Anne buys car, let's take Anne sells car. Here there are two examples, right? Here Anne buys a car and Anne sells car. If we split this sentence into frames, like Anne and for buys and car, and similarly for the second sentence, then there are modifier roles that are shared across these verb frames, that is buy or sells, which are somewhat similar to the non-core roles in a frame net. And there are optional frame elements such as an explanation, a purpose, a place, time, etc. that might add context to the relation. There are also other non-RE methods which are formally based on discourse representation theory, DRT, which considers a logical representation of text based on existential events. And according to DRT, the naming of Easter Island as a World Heritage Site is considered as an existential event where Easter Island is the patient or the entity affected, and a logical formula is generated. This logical formula is Neo-Davidsonian. It's this one. Here, this is the Neo-Davidsonian formula generated, and this backward E is known as for all. Here, in this formula, E is an existential term, and it refers to an NRE relation that we introduced earlier. And here the patient is the entity that is affected, which is Easter Island, and World Heritage Site is World Heritage Site names Easter Island. So this formula is also analogous to reification, which means directly define the context of edges themselves, which was introduced earlier in section 3.3. Here, to clarify what I explained earlier, the entity which is affected is Easter Island, and it's named as the World Heritage Site in 1995. And what neo-Davidsonian formula does is that the main predicate gets an even argument in one place, where it is a one-place event predicate. Then we posit thematic roles as two-place predicates relating the events and the individuals, as patient and naming of Easter Island as a World Heritage Site. Finally, when these relations are extracted in a closed setting, they are typically mapped directly to a knowledge graph. And the extracted relations are then set in an open setting, which may need to be aligned with the knowledge graph. For example, if the OIE process extracts a binary relation, Santiago has flights to Easter Island, it may be the case that the knowledge graph does not have other edges labeled as flights to. Where in alignment, it may rather map relations to edge, assuming that flight is a knowledge graph. But there are also other methods for such alignments that includes mappings and rules for aligning n-array relations, distributional and dependency-based similarities, association rule mining, Markov clustering, and linguistic techniques for aligning OIE relations. Here, if you look at figure 6.1, if the OIE process extracts the binary relation Santiago has flights to Easter Island, then it does not have other edges labeled as flights to, right? But in mapping such a relation to an edge, it can also mean the flight is in the knowledge graph.
This part is about markup sources. The web is interlinked markup documents where markers or tags are used to separate elements of the document. Most web use HTML. In addition to this, there are other markup formats too. Wikitext for Wikipedia, TeX for typesetting, and Markdown for content management systems. Here is the example of HTML document explaining about World Heritage Sites in Chile. On the left is source code document, and on the right is the formatted document. The left structured document looks right on the web. If we want to create or enrich knowledge graph using the information in markup documents, first we need to remove text and leave text alone so that we can apply techniques mentioned before as text sources. There are three technical categories for extraction. They are general approaches, focused approaches, and form-based approaches. General approaches work independently of the markup used in a particular format. It is often based on wrappers that map elements of the document to the output. Focus approaches target specific forms of markup in a document, mostly in web tables, lists, and links. Form-based approaches extract data underlying web page like deep web. These methods are easier to extract if you know the regularity of a particular web page. To explain with this example, this table is about World Heritage Sites in Chile, so we will likely find more World Heritage Sites for other countries following the same structure on that website. First method is wrapper-based extraction associated with general approaches. As I mentioned earlier, it is often based on wrappers. The meaning of wrapper in here is all methodologies that use pre-analyzed information about the structure of a particular site to extract information by accessing only the site. It locates and extracts useful information directly from the markup document. There are two types of approach. One is traditional approach and the other is modern approach. Traditional approach defines wrappers manually and it is weak for website change, so other approaches allow for automatically inducing wrappers. Modern approach is to apply distant supervision and it allows EL to identify entity on a web page and connect to nodes on a knowledge graph. Paths in the markup that connect pairs of nodes for known edges can be extracted, ranked, and applied to other examples. It is also used in LODIE, which stands for Linked Open Data for Information Extraction Project. This project is for exploring the usage of linked data for web-scale information extraction. This slide is explaining about the process of modern approach. Using EL, distant supervision can link Rapa Nui and World Heritage Sites like the nodes Easter Island and World Heritage Sites, and also can give the edge named. This approach can identify the candidate path. For example, assuming that X means one of the locations of World Heritage Sites, such as Easter Island and Rapa Nui, and that Y means the World Heritage Sites itself, this order represents the path from X to Y. First is TD, and going back, there is TR, and again going back, table and H1. This process can be implemented other TD tags at the same web page. Second is web table extraction. This approach targets specific types of markup, most commonly web tables. Many web tables are used in layout and page structures, and formats containing data can be different. So several procedures are required to extract only information we want. Our first step is to classify tables to find ones appropriate for the given extraction mechanism. Because a table that contains the real data and a table for implementing the structure visually can be present together. Second step is table normalization. To effectively show the table, row span, col span, and inner tables may be included and may be split vertically. The process of refining the table for effective extraction, including split tables, unnested tables, etc. Third step is identifying the main entity in the table. The main entity in the table can be found out elsewhere in the web page. Last step is linking to knowledge graph nodes. Associate cells with entities, columns with types, and column pairs with relations. Recently in this process, apply distant supervision to generate candidates for type and relation extraction. There are some useful tools for web table extraction. Statistical distributions can help to link numerical columns, and there are specialized table extraction frameworks for specific websites such as DBpedia and YAGO. YAGO is an open-source knowledge base automatically extracted from Wikipedia and other sources. This slide is about deep web crawling. Deep web is the part of the World Wide Web that cannot be searched using a standard search engines. Deep web crawling is the process of collecting hidden data by running queries through various search interfaces, including HTML forms, and it requires different crawling technique. To extract from deep web, we need to query sensible input for form, and those inputs can be based on user query or from reference knowledge, and then extract data from the generate response. The format about response will be markup documents, so apply same techniques mentioned before. From this slide, we'll talk about structured sources. Legacy data means old information that an organization has, especially information stored in an old-fashioned way, and this data is represented by two types, structured format and tree-structured format. The structured format is mainly tables, relational database, and CSV files. Tree structure format is mainly JSON and XML. Structure sources can be mapped to knowledge graphs, and the structure depends on the mapping. There are two steps for mapping process. First, we need to create a mapping from the source to a graph. Second, use the mapping to materialize the source data as a graph or to virtualize the source. This step means creating a graph view over the legacy data. Most structured content is stored as relational database format, and there are two types of mapping, direct mapping and custom mapping. The picture below is a relational database that we will use as an example. A direct mapping automatically generates a graph from a table. For each cell of the table, we can create edge like this only when non-header, non-empty, and non-null. X is the row of the cell, Y is the column name of the cell, and Z is the value of the cell. Looking at the example below, the highlighted cells are converted into knowledge graphs. And X typically encodes the values of the primary key for a row, so if we look at the yellow highlighted part example below, it represents the X nodes, and we can see the right one encodes the primary key for a row. But the left one is anonymous node because there is no primary key. And for Y, we can further encode the name of the table to prevent duplicate column names between tables, just like blue highlighted part. Also, can add a type edge based on the name of its table for each row X. For Z, can be mapped to data type values in the corresponding graph model based on the source domain. If in SQL the type is date, then it can be mapped X as date in RDF. This process is only possible when non-empty and non-null. Now we look at the difference between these two nodes. The longer node is using foreign key identified by the other node key value. Because foreign key exists and report.claimant references claimant.id, we can link the longer node rather than the other one. The longer one also has information about name and country. So far, we've looked at direct mapping in RDB. Processes are standardized for mapping relational databases to RDF. You can check this link for more information. However, there are another type of tables, CSV, and other tabular data. As part of mapping, it allows for specifying column names, primary or foreign keys, and data types. Automatic direct mapping can be applied on tabular sources of data and preserve the information of the original source. So, inverse mapping that reconstructs the tabular source from the output graph is also possible. But customized mapping is more recommended, such as to align edge labels or nodes with a knowledge graph. So, in this slide, we'll see the custom mapping. There is a declarative mapping languages which allow for manually defining custom mappings from tabular sources to graphs. A representative example is RDB to RDF mapping language. This language is proposed by W3C. It allows for mapping from individual rows of a table to one or more custom edges. Nodes and edges can be constants or individual set values. It is also possible to use templates that concatenate multiple set values from a low and static substrings into a single term. For example, this node is produced by the template ID and country. In addition, RTool RML allows for SQL queries to generate needed tables if desired output edges cannot be found from a single view. If we need the edges, the property crimes of US is 2, then we can send a SQL query. First, we need to join using columns climate and ID, and then grouping by country and applying count. The result is source node is US, edge label is crimes, and target node is 2. Of course, analogous standard for mapping CSV and other tabular data also exist. This slide is about second step of mapping structured data with knowledge graph. This step is to use the mapping to materialize the source data as a graph or to virtualize the source. There are two options. First is to materialize the source data. After mapping is defined, use them to materialize graph data following an extract, transform, load approach, whereby the tabular data are transformed and explicitly serialized as graph data using the mapping. Second option is to virtualize the source. This option is to use virtualization through a query rewriting approach. Queries on the graph are translated to queries over the tabular data. In this slide, we'll compare between ETL and QR. ETL is possible to use graph data like any other data in a knowledge graph, but the tabular data update status must be explicitly propagated to the knowledge graph. However, QR maintains only one copy of data to be updated. OBDA, which stands for Ontology-Based Data Access, is concerned with QR approaches. Below, there is a brief explanation about OBDA. The contents are as follows. Ontology defines a high-level global schema of data sources and provides a vocabulary for user queries. An OBDA system rewrites such queries and ontologies into the vocabulary of the data sources and then delegates the actual query evaluation to a suitable query answering system. I thought the underlined part was related to QR. For more information, you can check out the article below. Most QR approaches only support non-recursive entailments expressible as a single query, but some QR approaches support recursive entailments through rewritings to recursive queries.
This part is mapping from three structured formats among the two expression methods of legacy data. A number of popular data formats are based on trees, including XML and JSON. The content of tree-structured data can be more naturally represented as a graph using a custom mapping. Using GRDLL, JSONLD, RML, XSparkle allow for mapping in this way. GRDLL declares that an XML document includes data comparable with RDF. So if we use GRDLL, we can map from XML to RDF graphs. JSONLD is a JSON-based format to serialize linked data. It is primarily intended to be a way to use linked data in web-based programming environments, to build interoperable web services, and to store linked data in JSON-based storage engines. So if we use JSONLD standard, we can map from JSON to RDF graphs. RML stands for RDF Mapping Language. It is defined to express customized mapping rules from heterogeneous data structures and serializations to the RDF data model. So using RML allows for mapping from a variety of formats, including XML and JSON to RDF graphs. However, XSparkle is a hybrid query language which combines XQuery and Sparkle for transformations between XML and RDF. We can leverage existing knowledge graph to construct or enrich another knowledge graph, like DBpedia, Wikidata, Freebase, and so on. To extract relevant subgraph, we can use construct queries. In addition, entity and schema alignment between the knowledge graphs may be necessary to better integrate external knowledge graphs. An entity alignment means the task of linking entities with the same real-world identity from different knowledge graphs. We can use linking tools for graphs, external identifiers, or doing manually. Next part is schema ontology creation. In this section, we discuss some of the principal methods for generating a schema based on external sources of data, including human knowledge. We focus on the creation of ontologies using two approaches. First approach is ontology engineering, and the second one is ontology learning. Ontology engineering refers to the development and application of methodologies for building ontologies. By proposing principled processes, better quality ontologies can be constructed and maintained with less effort. There have been change of methodologies. As an early methodologist, waterfall-like process is one of the biggest features. Requirements and conceptualization were fixed before starting to define the ontology. After that, iterative and agile ways have been proposed because of situations involving large or ever-evolving ontologies. Diligent and Snommed City can be examples. More modern agile methodologies include extreme design, modular ontology modeling, and simplified agile methodology for ontology development. Such methodologies have two key elements: ontology requirements and ontology design patterns. Ontology requirements stands for specifying the intended task of resulting ontology or of the knowledge graph itself in conjunction with the new ontology. We can use competence questions to express ontology requirements. Competence questions mean natural language questions which illustrate the typical information needs. It can be complemented with additional restrictions and reasoning requirements. If we formalize the competence questions as queries over some test set of data, we can test ontologies. For example, assume that the competency question is, what are all the events happening in Santiago? Then it can be represented as the graph query as you see. Taking the figures, we can check if the expected result EID 15 is entailed by the ontology and the data. Because following the figure 2.1, EID 15's venue is Santa Lucia, and Santa Lucia's city is Santiago. Also, following the figure 3.2, venue and city are sub-property of location. So we can get EID 15's location is Santa Lucia, and Santa Lucia's location is Santiago. In this situation, we can assert that location's type is transitive. Transitive means that if we know y if x and z if y, then we can get z if x. So we get to know that EID 15's location is Santiago by expanding the transitive axioms. As a result, we can get answers containing EID 15 to that competence question. Ontology design patterns are another common feature of modern methodologies. This feature specifies generalizable ontology modeling patterns, which can be used as inspiration for modeling similar patterns as modeling templates or as directly reusable components. There are several pattern libraries have been made, like core event ontology pattern. Pattern libraries are ranging from carefully created ones to open and community moderated ones. The other approach for creating ontology is ontology learning. Ontology learning is used to automatically extract information from text, which is useful for the ontology engineering process. Extracting terminology that the relevant domains classes and extracting ontological axioms like subclass, disjoint, intersection of, etc. are all ways of ontology learning. The results of this learning process can serve as input to a more general engineering methodology. It allows us to validate the terminological coverage of an ontology, to identify new classes and axioms, and so on. That's all we prepared today. If you have any questions, please leave comments. Thank you for listening.